right, this is CS50, and this is the start of week 7. So today, perhaps thankfully, we begin our transition from the lower level world of C programming to the higher level world of web programming. And with that, we'll take a look at exactly how the internet works, what these machines and these internets that you've been using for years now actually do underneath the hood, toward a better understanding of how it all works and how you can make it work for you. Toward that end, why don't we take a look first at a clip from a TV show called Numbers that will get us started as to exactly how the internet works.
It's a 32-bit IPv4 address.
IP, as an internet.
Private network. It's a Meta's private network. She's so amazing.
Oh, Charlie.
It's a mirror IP address. She's letting us watch what she's doing in real time.
So, there is a whole lot of wrong with that TV show. So let's tease apart exactly one of the first such things and see if we can't wrap our minds around it. So the last frame of that movie, of that show, is this one here, which seems to suggest that this is what some hacker is using to get into some system. But no, if you zoom in on this source code, which is a language called Objective-C, in which iPhone apps, iPad apps, and Mac OS apps are written, you'll see that this is for some sort of drawing program that has a crayon as a variable. So, additionally, you might have noticed this address here. Now, this isn't as wrong, and this is probably deliberately chosen to be an invalid address so that it doesn't actually lead somewhere if a TV viewer actually visits it. But this number here, something dot something dot something dot something, is what's generally known as an IP address. And it's actually a good segue to this topic more generally known as IP, Internet Protocol. So, you've probably at least heard this phrase before, but what is IP, or Internet Protocol, as you understand it today? Odds are, if we asked for a show of hands, most of you have probably said the words IP address before, so what did you mean? What's that? Once more? The address of the computer. So that's exactly right. It turns out that every computer on the internet, and these days every phone in your pocket and tablet in your backpack, has an IP address, Internet Protocol address, which is a unique address that identifies it throughout the entire internet. Now, that's a bit of a white lie, because the world's actually running out of IP addresses, so we've started using private IP addresses, but more on that in a moment. But you can think of an IP address as like your postal service street address. We've used the example of Maxwell Dworkin, the CS building before, 33 Oxford Street, Cambridge, Mass. 02138, USA. That is its unique address in the world. Similarly, do computers have unique addresses? They just happen to look a little different. A number, dot, a number, dot, a number, dot, a number. And does anyone actually know what the valid range of numbers is for each of those hashes? Yeah. Exactly, 0 to 255. And even if you didn't know that, now draw a conclusion. How many bits are used to represent each of these numbers then? 8, apparently, because if the highest you can count is 255, that's an 8-bit value. So in total, an IP address is 32 bits. So fast forwarding to the mathematical conclusion, how many possible IP addresses are there in the world then? So that's 8 plus 8 plus 8 plus 8, so that's 32 bits. And we've always said that 2 to the 32 is roughly, okay, I'll field this one, 4 billion, right? And we talked about that in week 0 when we talked about phone books with crazy numbers of pages. But the short of it is that there's a finite number of IP addresses. And even though 4 billion might seem like a lot, we humans have been consuming quite a few of them for all of our servers and devices and so forth. So this is actually becoming a problem. Now, there tends to be a scheme behind who has what IP. For instance, many of the computers at Harvard have unique addresses that start with one of these two values. MIT similarly has a prefix, and a lot of companies and universities have their own unique prefix. And then most of us, for our home internet connections and the like, we share some prefix that Comcast or someone like that happens to own. And this is only to say that if you looked at most computers on campus, they'd probably have an IP address that looks like this. Now, you might also occasionally see an IP address that starts like this. In fact, if any of you grew up with internet access at home, and you were ever sufficiently technically curious to poke around your own computer settings, you probably instead saw an address that looked more like this, that started with 10 or 172.16 or 192.168 or some variants thereof. And that just means that the world has set aside a whole bunch of numbers to be private, which means you can use them in your home, you can even use them on your campus and within your company, but you can't use them on the internet at large. And so these private IPs have been a solution toward making sure that, at least so far as the whole world is concerned, we're not using that many IP addresses, but at least we can, on our own campus, have pretty much as many IPs as we want. But who cares? What's the relevance of all of this to an actual usage of the internet? Well, let's take a look at perhaps a simple picture here. Let me throw both of these up on the screen, and forgive my handwriting here, but if we think of ourselves as being this little laptop here, somewhere on campus, these days it has Wi-Fi, but in yesteryear, and if you find the right adapter, it can have an Ethernet cable, which would similarly let you connect to some kind of device. And you can call this any number of things, but I'm going to go ahead and call this for now, how about an access point? So this is my laptop. This is my AP or access point, and this is some wireless device, not unlike the ones that Harvard has all over the ceilings and walls around campus that have blinking lights and that are what your laptops use to talk wirelessly to the rest of the network. So somehow this laptop is talking to that thing on the wall in the dining hall or elsewhere. Now, meanwhile, that access point is connected to something else on campus, and it's probably something known as a switch. And they look a lot more interesting than just these box diagrams, but somehow that thing's connected to a switch, and in turn, somehow that switch is connected to a device that's probably a bit bigger, called a router. And then meanwhile, Harvard is connected to the entire internet, which we'll draw as this cloud here, via some number of wires or wireless technologies. So there's a lot of steps between me and the rest of the world, and indeed, even within this picture here, there are some other servers or services involved. And I'm just going to draw these somewhat abstractly, just so that we have the acronyms before us. One is called DHCP, and another one, a little more interestingly for today, is called DNS. So these are servers that are somehow accessible to my computer as well. So now let's tease apart a bit of jargon. So the access point is just this wireless device, often with antennas, that actually lets you talk to it wirelessly. At home, you might call this a home router. It might be made by Linksys or Apple or D-Link or any number of companies. That, in turn, is connected to a switch of some sort. Or back home, what is your Wi-Fi device probably connected to instead? Because you probably don't own all of this equipment. Yeah, a cable modem or a DSL modem back home that you got from Verizon or Comcast or one of those carriers. So think of all of this complexity as supporting a university or really a business like Comcast, and really the stuff that's in your home is probably on this side of the fence, plus maybe one of these cable modems or DSL modems they might provide. So a switch is just a device with a whole bunch of data jacks in it. In fact, if you recall that news report we played on the big screen a couple of weeks ago, where we were talking about shell shock and how bad this bug was, and there were all of these photographs of cables and jacks and things that looked technical, those were just dumb switches that just internet connect computers by plugging cables into them. So that's all a switch is. And now these devices get a little more interesting. DHCP, if you've poked around your computer at home or even on campus, you might have seen this acronym. Does anyone know what a DHCP server is? Dynamic Host Configuration Protocol? Not the kind of thing you really need to write down. DHCP? Anyone at all? All right, so let's rewind the story. If the story here at hand is predicated on my having a unique address in the world, an IP address, where does that come from? In yesteryear, when you got to campus, you actually had to ask someone at Harvard, what should my IP address be? And you would manually type it into your computer. But more recently, technologies exist that allow you to dynamically, DHCP, get an IP address simply when you plug into campus wirelessly or with a wire. So a DHCP server is just a server that gives your computer a unique IP address, somewhat randomly or via some algorithm. But if you think back a few weeks or a few years, when you first registered your computer on campus, you were telling Harvard, authorize me to give me an IP address. Now, DNS starts to get a little more interesting. Domain name system. And does anyone want to take a stab at what this thing is here? It's one or more servers that perform a fairly simple task that's kind of important. Yeah. Yeah, it translates URLs to IP addresses and vice versa. Consider, after all, that when you go on a website, you type in something like facebook.com or google.com or harvard.edu. You certainly have never typed, most likely, a numeric IP address. And you can think of the reason why back in the days, and even now to some extent, when you make a telephone call to a company, they really try hard to buy themselves an 800 number that actually has words in it, like 1-800-COLLECT, or something that's memorable like that, so that people don't have to remember what COLLECT actually expands to. So we've seen this heuristic in the past, and indeed that's what IP addresses and what we'll call host names, or fully qualified domain names, do for us. It allows us to address servers by words instead of numbers. So how do we actually see this conversion? I'm going to go ahead and open up a program. I'm just going to go ahead and open a terminal window, and I'm going to go ahead and show you what a DNS server does. For instance, if I wanted to see what the IP address is of Facebook, I can type at a terminal prompt like this, and you can do this even inside of your appliance, nslookup facebook.com. And I see a bunch of things. This first response is Harvard's DNS server, that picture that I've drawn there, that's telling me that Facebook's IP address is apparently this. So let me go ahead and copy that, 173.252.120.16, and let me open up Chrome on my Mac, and let me go to http:// and paste that IP address in and hit enter, and indeed, I find myself at Facebook. So somehow that conversion indeed happened. And if I do this again, let's do nslookup www.google.com, I get back a whole bunch of responses. And indeed, there's different ways that companies implement this. Sometimes they tell the world they have one IP address, but that one IP address gets resolved or mapped to multiple servers. Or in the case of Google, they tell the world, we have a whole bunch of IP addresses. Your laptop is welcome to contact any one of these servers. So all of that's been going on underneath the hood. When you type in www.google.com, enter into your browser, and in turn, your operating system, Mac OS or Windows or Ubuntu Linux, ask the nearby DNS server, what is the actual address of this server? Because the last device in this picture, a router, is the one whose purpose in life is to route information, route packets, so to speak, envelopes of digital information containing zeros and ones from sender to destination, from origin to receiver. And so a router routes stuff. So why is this all particularly relevant? Well, let's take a look at how this might be used. Suppose that I have here a picture of Rob Bowden. All right. So suppose that I want to send this picture of Rob Bowden to Dan in the back of the lecture hall. So I am a computer, like my laptop, and Dan is some other computer on the internet, and I want to send a packet of information from me to him. That begs the question, how do I actually route this packet to him? Well, in human terms, I would say, hey, can you pass this to Dan? And then a bunch of you would probably pass it back and forth, until it eventually makes its way over to Dan. But that's a little imprecise. Computers probably need to be a little more methodical, so probably Dan has an IP address. So what really I should do is I should take, for instance, a blank envelope like this, and I don't know what Dan's IP address is, so I'm just going to generalize it as Dan's IP. And I'm going to put this in the to field of my envelope. And meanwhile, I have an IP address. It doesn't matter today what it is. So I'm just going to say my IP in the back corner there. And then I'm going to go ahead and put this picture inside of this envelope. And then each of you, presumably, as routers on the internet, have been pre-configured by humans generally, or sometimes by automated algorithms, to know that if Dan's IP address starts with a 1, it should go that way. If Dan's IP address starts with a 2, it should go that way. Maybe a 3 goes that way. Maybe a 4 goes that way. And that's a little overly simplistic, but that's the general idea. Each of these routers, and there might be as many as 30 between me and Dan, have some kind of spreadsheet inside of their memory, a database table that just says, an IP address that looks like this goes this way. An IP address that looks like this goes that way. And that's how it makes fairly simplistic decisions. But it turns out that these routers do something more than that, potentially. They allow computers to guarantee delivery, at least with high probability. So you might too have heard, even if you've never quite cared or wondered what it is, you might have heard of something by this acronym. Let's go back over here for just a moment and pull up this, TCP. Transmission Control Protocol, another technical way of just describing another technology that's used on the internet. So IP, Internet Protocol, is used for addressing. It's some standard that the world came up with that said you put one IP address here for Dan and one IP address here for yourself, and then you put some information in an envelope. But TCP is another technology used in conjunction with IP. And indeed, if you've ever seen these acronyms before, you've probably seen TCP/IP, which just means people tend to use them together. Well, TCP is kind of cool because it allows you to increase the probability that the data is actually going to get from me to Dan. In fact, the internet is a crazy place. There's no guarantee that if I send data this way, that it's going to go that way next time around. It might go that way or that way. The shortest distance between 2 points is not necessarily a straight or the same line. Moreover, some of you guys might make mistakes or get overwhelmed with too many envelopes coming your way, so you just kind of give up and literally drop some of these envelopes on the floor, and in that same way can data be dropped on the internet by routers. So to decrease the odds of this, I'm going to take my little safety scissors here and cut Rob into, let's say, 4 pieces, 4 segments. And now I'm going to go ahead and put one more piece of information on this envelope. I'm going to say something like 1 of 4. So now my final envelope, at least the first, looks like this. I'm going to go ahead and put this one in here. And for time's sake, I'm going to label the others identically as 2 of 4, 3 of 4, 4 of 4, again with Dan's IP address in the front of it and with my IP address on the back left. But I can't send them just yet, because it turns out that on the internet, servers can do multiple things. In fact, we all might use the web quite a bit, the World Wide Web, http:// whatever, but there's other services on the internet. What are some other services, sort of user, consumer-friendly services that spring to mind besides a web browser-type program? Email. OK, good. What's another one? So chat, whether it's Skype or GChat or something like that. So some kind of storage service, certainly, something like Dropbox or Box or the like. So there's different services on the internet. And it turns out that Dan, if he is indeed a computer, doesn't have to be dedicated to one thing in life. He can actually do multiple things. And indeed, he can be an email server. He can be a web server. He can be a chat server. But that seems to suggest that Dan needs to know in advance what are the contents of these messages. Is this a web page I'm sending him? Is it an email I'm sending him? Is it an instant message I'm sending him? So we need one more piece of information on these envelopes so that Dan, when he receives this envelope, knows what program to use to display it. Is it a browser? Is it Google? Is it Skype? Or is it Outlook or some other program altogether? And so with TCP comes just a human convention. The world decided some years ago to associate unique integers with the most popular services. One's called File Transfer Protocol, FTP, though it's a little dated now, but its unique identifier is 21. SMTP, for outbound email, its unique identifier is 25, just because. DNS, the thing we talked about earlier, uses the number 53 for its queries, like what is the IP address of Google.com. And now the more familiar, you might have somewhere at some point seen the number 80, and maybe 443. Those are the unique identifiers for HTTP, which is the language we'll soon see used for web traffic between browsers and servers. And 443 is for the secure version thereof. So the one last detail I'm going to put on my envelope is that I'm not going to send this just to Dan's IP. I'm going to send it to, say, :80. If what I'm trying to send him is a web page that contains Rob Bowden's picture. So I'm going to do the same thing on these other envelopes, and then ultimately, I'm going to drop these off with the nearest router, recognizing that that router might not necessarily take the same path every time. In fact, I might have the first packet going this way, second packet might go that way, third packet, start routing, might go over here. And in theory, can't keep it. In theory, all 4 of these packets should eventually route their way, however efficiently or inefficiently, all the way to the back, at which point Dan, upon receipt, can reassemble them based on... The funny thing is, we all know what the outcomes here is going to be. Dan's going to get a picture of Rob, but let's see how this works out. Well, rather, Dan's going to get part of a picture of Rob. Very good. Everyone's participating today. All right. So as Dan starts to receive these packets, let's ask one question. What if one of you gets lazy, overloaded, malicious, or just powered off, and one or more of the packets doesn't make it to Dan? How is Dan going to know he did not receive one of the segments of the 4 I sent him? Just intuitively, what can we do? Yeah? Exactly. Because I've uniquely numbered them and I've specified how many segments there should be, he can infer from that which, if any, of the segments he's actually missing. And what TCP tells computers to do, if computers like Mac OS and Windows and Linux support and understand TCP, which they do, TCP's documentation essentially says that Dan should send me a message back saying, hey, David, I'm missing packet number 1 of 4 or 3 of 4, whichever it is. And then my job is to take another picture of Rob, which we have extras of for later today if you'd like to take one with you. And then I can resend that segment of Rob all the way to the back. So as simplistic as this mechanism is, that is what's happening almost any time you do something on the internet, particularly for these most popular of services. There are other protocols, other technologies besides TCP that work a little differently, but so many of the services we typically use actually rely on these protocols. So Dan, did you get the full picture back there? Yes, we have reassembled Rob in the back. Thank you so much to the routers. Suppose I actually wanted to see the routers between me and MIT, much like you guys were the routers between me and Dan. Well, rather than NSLOOKUP for name server lookup, I can instead type traceroute, which is actually going to do what it says, and I'm going to do it in quiet mode with -1. It's a command line argument that just says try this once and not multiple times. And now I'm going to type www.mit.edu. Now the output is fairly quick and cryptic, but what's neat about this is that each of these rows essentially represents a student in this audience, if you were the path between me and MIT. What you see up here first is the domain name that I typed in, or the fully qualified domain name as it's properly called. And this apparently is the IP address of www.mit.edu. My computer figured that out for me. This here is a promise that we're only going to try to reach MIT within 30 hops. There better be no more than 30 students between me and Dan. And now each of these rows represents literally a router between me and Dan, literally one of you guys. And so this one doesn't seem to have a name, a domain name. It just has an IP. And it only took 0.662 milliseconds to get from me to that first router. The next one wasn't that much farther away. It only took 1 millisecond to get there. And now, thankfully, things get a little more user-friendly with names that are cryptic but a little more telling. This apparently is a router in the core of Harvard's network, housed, only because people have told us this, in the Science Center, SC. And GW is just shorthand notation for gateway, which is a synonym for router. So this is some system administrator's super cryptic way of naming one of the servers in the Science Center. Meanwhile, that server is apparently connected by some kind of cable to another router that's nicknamed border gateway 1-something, whatever those numbers mean. And then apparently Harvard has a connection that's another millisecond away to something called the Northern Crossroads, which is a common peering point between big places like Harvard where lots of cabling goes in and allows interconnections among different entities. Step 6, unfortunately, doesn't have a valid name. And step 7 gets interesting. I have no idea what most of these mean, but NY does jump out at me. And what does that probably signify? It's not even technical, just New York. So indeed, what's common human convention, not guaranteed, but common convention is to name routers by nature of the city or the airport code that they're nearest to. So with some probability, this router, number 7, is probably indeed in New York. And this seems to corroborate that assumption because it's 6 milliseconds instead of just 1 or so to something here on campus. But now, take that into account, right? On like Megabus or whatnot, it might take 4, 5, 6 hours to get a human from here to New York. To get a piece of data, it takes just 6 milliseconds to get a packet from me to Dan if he were all the way in New York. Then finally, this apparently is the actual domain name for www.mit.edu. They've apparently outsourced their web servers to a company called Akamai, which means some other company runs their servers, and that's why we're seeing that weird thing there. Well, let's do this once more. Let's go ahead and do a trace route to our friend Professor Nick Parlanti at Stanford, who has a server called nifty.stanford.edu. Enter. And now we'll see probably a slightly longer path that goes through a few more cities. So here are these nameless Harvard servers here. We're in the core of Harvard, the border gateway of Harvard, the Northern Crossroads, wherever this is. And now it's getting a little more interesting. I'm guessing that router number 8 is in what city? Chicago, probably, based on this thing here. And now we have Salt Lake City, maybe Los Angeles here. And then LAX, yep, this probably is LA by the bottom, until finally it goes from Southern California all the way up to Northern California to where Stanford is in Palo Alto. So pretty cool. And let's take this one step further. It apparently would take you 82 milliseconds to send a message to Dan if he were in California instead of New York. Let's do something like trace route one attempt to www.cnn.co.jp for the Japanese version of CNN's website. And now we're still in Boston, it seems, at the moment. A couple servers 6 and 8 aren't responding because they're being a little private. But eventually, there seems to be something interesting going on between, let's say, steps 7 and 9. What is probably between 7 and 9, and certainly between 7 and step 17? There's a huge jump in the amount of time it's taking for data to go from one of these hops, one of these routers to another. So odds are somewhere in here, there's probably, especially right here, there's probably a very large body of water that has some trans-Pacific or transatlantic cable that actually requires even more time for data to get from one point to another. But again, imagine the hours it would take to fly to Japan. Here, in some 200 milliseconds, boom, your message is actually there. So you can play around with this on the appliance or even in Windows or Mac OS with slightly different commands. Sometimes you will get these stars, like in rows 6 and 8, which just means the routers are configured not to give you an answer for privacy's sake. But generally, this technique would in fact work. So it turns out, too, there's other juicy information lurking in tools that you take for granted every day. So for instance, if you receive an email, frankly, as some of you may have recently, of questionable origins, if you've never looked at Gmail's interface before, whether it's for the college interface or your personal one, you might see your inbox looking like this. And in fact, this is an email I sent, mailin@harvard.edu, to jharvard@cs50.harvard.edu this morning, just so I could take a screenshot. But it turns out all this time in Gmail, there's that little triangle toward the top right there next to the Harvard crest that if you click, you can click Show Original. And if you do that, you'll actually see a bunch of very esoteric information like timestamps and IP addresses and domain names. But you'll see, in short, the headers that all this time have been hidden in each and every email you send and receive. And it's these headers that people can use, computer scientists or otherwise, to actually infer with some probability where and from whom an email actually came. In fact, we'll talk in later weeks about how email itself can be generated programmatically, which is a very good thing for a website that wants to send emails to users. But we'll see, too, just how trivial it is to forge emails from someone to someone else, unless you actually know how to verify the headers, and even that is a losing proposition these days. So with that said, let's go one layer up. We started with IP, which addresses packets for us, gives them unique addresses. TCP, which in short guarantees delivery, or at least increases the probability thereof, by adding things like segments, 1 of 4, 2 of 4, 3 of 4, and 4 of 4. And now let's layer on top of that another protocol. All of these things are protocols, computer conventions that dictate how two computers talk to one another. HTTP, finally, today, is Hypertext Transfer Protocol, and this is the protocol that web browsers use when speaking to web servers. So when you pull up a browser like Chrome or IE or Firefox or Safari or whatever, and you type in something like facebook.com and hit enter, not only does your computer first translate facebook.com into what? An IP address. It then sends a message to that IP address saying, give me today's homepage, or give me the login screen of Facebook, or if you're already logged in, give me the default view of my timeline. So that's what HTTP says. And more colloquially, if I am a web server and you are, what's your name again? Margot is a web server, and I'm a web browser, and I simply want to retrieve my timeline from margot.com, I would say, like, hello, I'm David.
Hi, I'm Margot.
And you would then respond with additional information to me. So we have this stupid human convention, for instance, thank you, of shaking each other's hands, and computers have that same idea, where a client, like a browser, asks a server to do something on his or her behalf. And so here's a picture, for instance. On the left is a computer, laptop, desktop, whatever, or even a phone. And on the right is a very dated view of a server. They typically look smaller and sexier these days. But the point is simply that there's some kind of communication between client and server. And client in the sense of someone in a restaurant and the waiter or waitress, same idea with computers. Clients and servers, one asks for information, one responds with information. Now, how does that information come back? Well, consider this. Get is sort of the default way And it's a super simple term that just dictates how a browser gets information from a server. In other words, rather than just goofily extending my hand to Margot, if I really were a browser, I would stuff inside of an envelope, as I did with Rob's photo before, a textual message that literally says something like this: get/http/1.1 host www.google.com or margo.com or whatever the server's name might happen to be. And then ... some other stuff. But literally inside of an envelope would be a fairly simple textual message like that, that upon receipt, Margot would open up, read the contents, and respond accordingly. Now, it's a little non-obvious with this example, but get slash. What is the slash probably referring to, just based on your familiarity with browsing the web in daily life? What's the slash? An escape sequence, not a bad idea, but generally escape sequence go the other way. That would be a backslash usually, but not a bad thought. Yeah. A pointer, also a good thought, but not, even simpler than that. The home directory, the root of the hard drive, so to speak. Most of us don't type this, but technically, if you wanted to be super proper these days, you would go to something like http://www.facebook.com/. Now, I say most of us wouldn't bother typing the slash, and frankly, most browsers, Chrome included, don't even bother showing us the slash these days, just because they like to be simple and succinct. But the slash just means go to www.facebook.com and get slash, the root of the hard drive, the default page in facebook.com, using what protocol? Well, using version 1.1 of this thing known as HTTP. The server, or Margot, and by the way, do you mind that I'm using you? OK, so we're good now. So Margot responds now with an envelope of her own, inside of which is a similarly textual message, the first line of which is, yep, I speak HTTP version 1.1. 200 is a status code, which just means all is OK. I have the page you're looking for. Meanwhile, content-type:"text HTML. This is Margot's semi-arcane way of saying, what you have requested is a web page, and it's type, so to speak, almost like a variable sense, but this is much higher level now. Its data type is text, but specifically HTML, the language we'll soon see. And then there's some other stuff. So other stuff is literally what Facebook is responding with. So let's see this too. Let me go ahead and open up Chrome on my laptop, which you can do on your own computer as well. And I'm going to go ahead and open up www.facebook.com, enter. And I get this familiar screen here. But now I'm going to do something else. I'm going to go ahead and go to View, Developer, and go to Developer Tools, which you should have within Chrome on your computer, or at least within your appliance. I'm going to scroll this thing up here, and you're going to see a whole bunch of cryptic text here. It turns out that what Margot put inside of that envelope in response to me is a language called HTML, Hypertext Markup Language. It's not a programming language, because it doesn't have loops and conditions and functions and things like that. It's a markup language in that it has special syntax called tags and attributes that tells a browser what to display on the screen and how to display it. Should it be centered? Should it be bold-faced, red, green, blue? It's a markup language in that it tells a browser what to show on the screen. So this is literally all of the HTML and more that Facebook's server is spitting out, and that Chrome and IE and Firefox have been designed by their respective authors to understand. And in fact, it's a little messier than that. If you instead go to View, Developer, View Source, this is actually what Facebook is outputting. Sort of 0 for 5 for style, right, if we infer that this probably isn't the best. But frankly, they can get away with it, because if you're serving up billions of web pages per day, you really don't want to waste time and bytes and money, ultimately, in transmitting things like new line characters and spaces and tabs, because you're just spending for bandwidth unnecessarily with your ISP. So indeed, this is meant to be minified in this way. But what Chrome is doing for us is it's taking this HTML, which completely looks like a mess and unintelligible to a human, and it's just formatting it. It's pretty printing it so that we can wrap our minds around it a little more readily. But more interesting is this. If I now click in Chrome, not Elements, but Network, I'm going to see a little logging screen that's going to show me all of the HTTP requests that are actually going back and forth between me and Facebook, or me and Margot if I make more than one request. So I'm going to go ahead and click the reload icon up here in Chrome. And now a whole bunch of stuff flew past at the bottom. I'm going to scroll back up to the very top. And now notice this. The very first request my browser made was to www.facebook.com. It's using the get mechanism, which just means it's speaking the textual language that we saw an example of a moment ago. And moreover, it turns out that the response that Facebook gave me is 200 OK, which means I found the web page in question. If I click on this row, I can actually see those headers a little more clearly. These will make more sense before long, but notice that my browser sent a whole lot of information, like host and method and cookies. We'll come back to those before long, and you'll finally understand what a cookie actually is and how you soon will be sending them. And you can see what Facebook is sending back, including the content type of text HTML, the current date time, its privacy policy or lack thereof, and then finally a number of cookies that are being set on your computer as well. But we'll tease those apart before long. But in short, every time you visited a web page now for years, you've been sending messages like the one I sent in an envelope to Margot and to Dan, and you've been getting back responses like this from Facebook. But moreover, guess what's being disclosed to Facebook and Google and everyone else every time you visit a web page? What is on the outside of every envelope your computer has been sending? Your IP address, right? Maybe not your name per se, but your IP address. And just let's connect the dots later. If you're using services like the web or BitTorrent and the like, and you've registered a computer at a place like Harvard, someone somewhere knows that John Harvard's IP address is this.this.this.this. And indeed, logs can be kept both on a campus like this, on a Comcast network, on Verizon, or frankly at the NSA, as we've recently learned, that logs pretty much everything that you are doing on the internet. And we'll come back to this in a future class on the implications of these design decisions and security, but the truth is you really don't have all that much privacy. Every time you've been visiting anywhere on the web, you've been showing your hand and revealing at least your IP address. So, scary note aside, what can we do to embed things like cats in a web page? So we have a bunch of responses that might come back from the server, and we won't see all of these today, but 200 is good, and you've probably not seen all of these as a human before, but you've probably seen at least one of these. Which one of these might look familiar? So 404, file not found. And indeed, you're going to see this programmatically yourself. 404 just means the file you requested, slash or slash something, simply doesn't exist. And a web server typically responds with 404 as a result. Meanwhile, we'll soon see that the contents of that message are this language known as HTML. And this is a super simple snippet of HTML that does nothing other than display hello world on the screen. Indeed, you see at the top of this something called a document type declaration, which just says, hey world, this file contains HTML. And then the next bit of HTML that you're going to write, it has an open bracket and then the word HTML, then a close bracket, and then open head and close bracket. So in short, let's actually do this more mechanically. Let me go into my appliance, but you can do this anywhere that you have a text editor too. I'm going to go ahead and save a file called hello.html. I'm going to put it on my desktop to keep things super simple right now. And I'm going to do exactly what I just saw. So doc type HTML, open bracket HTML. And now notice I'm going to do the opposite preemptively. And by opposite, I mean the same tag, so to speak, but it starts with a /. And then over here, I'm going to say head, because it turns out that every web page has a so-called head, which is stuff that goes in the title bar and at the very top of the page. Indeed, title is just going to be hello here. And now I'm going to have a body to this web page. So every web page has both a head up top and a body, which is the guts of the page. And here I'm just going to say something like hello world, and I'm going to save this file. If I now minimize gedit, look, there's a little file on my desktop called hello.html. Now, that's not on a server yet, per se. Indeed, it's just on my own personal desktop here. But if I open up Chrome and hit Control-O, there's the count in question, and I go to my desktop, and I open up hello.html, there, in fact, is my super simple web page. The body of my page in this white window here is the body with hello world, and the title in the head of the page is in the tab there. And we're going to see soon that it's super simple to open up other pages as well. For instance, I'm going to go into some of the distribution code for this week, source 7, and I'm going to open up not the JPEG, which this guy is here, but I'm going to open up image.html, which ultimately looks like this. But let me now open this up in gedit and go into Dropbox, source 7, and image.html. Most of this is just comments, as we'll soon see. But if I want to put Grumpy Cat inside of this web page, it suffices to put another open bracket, and then the keyword image, or IMG for short, and then alternative text for accessibility reasons if someone has a screen reader or something like that. Source, which is what's the name of the file. Cat.jpg. And then because this tag's a little special, we put the /, as we'll see, inside of the tag. But the end result is a web page that looks like this. So in short, what we're going to be doing now over time is using the web and creating web pages to ultimately be containers, not only for silly things like images and links and tables and bulleted lists and the like, but also to give us ourselves a graphical user interface, a GUI, not unlike what we did with Breakout. But within this environment, we're going to start using languages like PHP and JavaScript, a database language called SQL, a client-side scripting language called JavaScript, to actually create all the more dynamic interfaces, but in a much, much more familiar context. But before then, let's conclude today with a look, as promised, of what's really going on underneath the hood with the internet itself. Stipulate for today that the internet can be used to transfer things like web pages over HTTP, much like I shook Margot's hand earlier. But there's so many other services that use TCP and IP that we take for granted that work, as we'll see here in this film that'll take us to the end today.
For the first time in history, people and machinery are working together, realizing a dream. A uniting force that knows no geographical boundaries without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Want to know how it works? Click here to begin your journey into the net. Now, exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information and how to package it. Now, the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Because this particular packet is going out onto the internet, it also gets an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. The LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. The highway of the LAN is packed with all types of information. These are IP packets, Novell packets, Apple Talk packets. They're going against traffic, as usual. The local router reads the address and, if necessary, lifts the packet onto another network. The router, a symbol of control in a seemingly disorganized world.
Whoops, sorry about that. Let's put this one here, this one here. This one's here, this one goes here. I don't like this one. Let's go this one, let's switch here. This left, let's move this one here. Let's put a channel here. Let's put that one here. Let's put that one here.
There he is, systematic, uncaring, methodical, conservative, and sometimes not quite up to speed.
Sorry.
But at least he is exact, for the most part.
That one goes there, that was there, that one goes there, that one goes there, and this one goes there. And that one goes there, that goes there. He's fine. Let's go back, that goes there, that goes there.
As the packets leave the router, they make their way into the corporate intranet and head for the router switch. A bit more efficient than the router switch plays fast and loose with IP packets, deftly routing them along their way. A digital pinball wizard, if you will.
Here we go. Here comes another one. And it's another. Watch this, Mom. Here goes. Whoop, we're on the back. Hey, in there, in there, in there. Over the left, over the right, over the left, over the right. You got it. Here it comes. Right on. He shoots. He scores. It's going. Hey, wait. Hey, watch out. Here comes another one. Oh, here we go. And it's gone. It's gone.
As packets arrive at their destination, they're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. The proxy opens the packet and looks for the web address, or URL. Depending upon whether the address is acceptable, the packet is sent onto the internet. There are, however, some addresses which do not meet with the approval of the proxy, that is to say, corporate or management guidelines. These are summarily dealt with. We'll have none of that. For those who make it, it's on the road again. Next up, the firewall. The corporate firewall serves two purposes. It prevents some rather nasty things from the internet from coming into the intranet, and it can also prevent sensitive corporate information from being sent out onto the internet. Once through the firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. Now you might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. We are now ready to enter the world of the internet. A spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your LAN. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded ping of death. A special version of a normal request ping which some idiot thought up to mess up unsuspecting hosts. The paths our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest or shortest routes possible, but they will get there. Eventually. Maybe that's why it's sometimes called the worldwide wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat. Literally. And all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall could be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. Port 25 is used for mail packets, while port 80 is the entrance for packets from the internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. Now, the firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet.
It's okay, Norm. It's okay. No problem. Have a nice day. Be out of here. Bye.
For those packets lucky enough to make it this far, the journey is almost over. It's just to line up on the interface, to be taken up into the web server. Nowadays, a web server can run on many things, from a mainframe to a webcam to the computer on your desk, or why not your refrigerator? With a proper setup, you can find out if you have the makings for chicken cacciatore or if you have to go shopping. Remember, this is the dawn of the net. Almost anything's possible. One by one, the packets are received, opened, and unpacked. The information they contain, that is, your request for information, is sent on to the web server application. The packet itself is recycled, ready to be used again, and filled with your requested information. Addressed and sent out on its way back to you. Back past the firewall, routers, and on through to the internet. Back through your corporate firewall. And onto your interface. Ready to supply your web browser with the information you requested. That is, this film. Pleased with their efforts and trusting in a better world, our trusty data packets ride off blissfully into the sunset of another day, knowing fully they have served their masters well. Now, isn't that a happy ending?
That's it for CS50. We will see you next week.
Let's rage!
I knew you were gonna come to me. And here you are, but you better choose carefully. 'Cause I'm capable of anything, and everything. Make me your Aphrodite, make me your one and only. Don't make me your enemy, your enemy, your enemy. So you wanna play with magic? Boy, you should know what you're falling for. Baby, do you dare to do this? 'Cause I'm coming at you like a dark horse. Are you ready for a perfect storm? 'Cause what's in mind,
There's no going back.
Mark my words, this love will make you levitate. Like a bird without a cage. Down to earth, if you choose to walk away, don't walk away. It's in the palm of your hand now, baby. It's a yes or a no, no maybe. So just be sure before you give it all to me, all to me. Give it all to me. So you wanna play with magic? Boy, you should know what you're falling for. Baby, do you dare to do this? 'Cause I'm coming at you like a dark horse. Are you ready for a perfect storm? 'Cause what's in mind,
There's no going back.